Yo, what up? Is this thing on? Can you guys hear me? Hello? Hello? Okay, cool. It's working. Okie dokie. Welcome, welcome. Gonna get started digging into what I crashed on last time. I think it was Tuesday. Uh, been dealing with some weird issues with my system, particularly Wayland crashing. At least I think I've narrowed it down to Wayland, but who knows? So if my system crashes, then that'll probably be the end of the stream. If not, then we'll keep going. Hopefully hit the 2.5 hours that we normally do. Um, Last we left off, I was racking my head over the message values that get sent to the device when we're trying to set the main brightness. So when I was looking at the packet values or the message values in the actual Wireshark capture, it showed a max value that was being sent of 64 in hex, and something that was throwing me off was the 75% value was 4B, I think. And what I've come to the conclusion of is that it's a we're running into a confusion between Wireshark interpreting uh, the HID data as hex, and then the device expecting byte data, and then also Python trying to convert our actual command data into the right data type for the device. But what I've got open right now is a conversion chart from decimal to hex to characters, and ASCII and everything, all that other good stuff. So if we look at 64 being the max value that gets sent to the device, it looks like that results in a hex character of 40, and that is an ASCII character of at. This may not be the right we may not be on the right track with this, because when I look at the packets for let me just get Windows open. I'll show you guys. Um, when I get uh, when I look at the packets for the max value, Wireshark interprets that as the ASCII character D. And I could just be confused. So let me get this open. Do do do. There we go. All right, come on, Wireshark. Um, yeah, it's gonna take a second to open. So let's see. While we're waiting for that to load, I'm just gonna mess around with a little bit of these commands, or mess around with this command and see if we can get the data spit out right. Looks like it's still loading up. Okay. So what I was doing last was just testing the message, just to see if that would get packed properly. Let's get a new window open. And I just want to make sure that I'm still okay. Cool. I'm still shortcutting that. And calling get mean brightness. So run this again. I don't think the device is actually hooked up. I do this all the time. Oh, I've already got it attached to the Windows device. Okay. And let's see if that turns it on. I've been having some issues with it not actually turning on, so I don't know what the deal is with that. But that's okay. What I've had to do is like, uh-oh. See if it actually plays nice. Alright, well, while it's thinking about it. Emulator, let's see, we want brightness changes. And we're looking for the shit all the way down here. There we go. So, 64. Let's see if maybe I'm just interpreting that wrong. And then this 32. Yeah, okay. Yeah, it looks like libvirt messed up on me. One moment. Oop. Alright, let's try this again. Alright, we'll add our USB device to the Windows host. And let's see what this does. Alright, let's see if that'll turn it on. No? Alright, we'll get the driver running then. See what that does. No device connected. Okay. Well, let's unplug it. Plug it back in. And we'll see what this does. Oh, there we go. Okay, now it's turning on. Alright, cool. Alright, cool. Just want to get that going. I actually don't want that running in the background. And kill that one too. There we go. That one. That's the big one. Okay, cool. Yeah, so looking at these values, 4B, this K right here, this is the 75%. We set the brightness to 75%. This is brightness at half. This one is brightness at full. So let's go back to Linux and take a look at that chart again. Yeah, so the letter K, 4B, that's 75. That makes sense. Okay, so it is 64 in hex should be the letter B, right? Lowercase b. Or is that 62? Oh, D, sorry. Okay, so maybe it's actually going 0 through 100 in decimal. So what we can probably do is take our value 0 through 100 percent and convert that value of the percentage into a hex value, and then that will give us the appropriate character. So let's try that. So what we need to do, max brightness is 100, value, set that at 100, and then, wait a minute. Yeah, okay. I think that makes sense. And then we need to convert this into hex value. And that's probably not gonna, it's probably not gonna like this. We need to change that to something else, but we will see. Oh wait, do I need to convert it into, let's just convert it into a character, because I think that might be better. What is that, oct? What is it, Python, CHR, okay. Because then when we pack it in as a character, that should work. So let's go ahead and I want to detach the device from Windows now that it's running. And then we will go ahead and attach it to Linux. All right, and then let's go over here, LSUSB. All right, so we've got our mount and display pad. And let's go ahead and run our code and see what this does. Should set the brightness to max. Oh, connect and handle to OBS WebSocket. Okay. Let's see. Probably need OBS running as well, just so it doesn't whine. Okay. Character format requires a bytes object of length 1. Okay. So do I need to take this and let's do so it gives us the letter D. So can we do 2 bytes? String object has no oh, is it just bytes? Bytes, bytes, bytes. Bytes. Let me just look it up. I always cannot remember this crap. UTF-8, okay. So string.encode UTF-8 is probably, that'll probably work for us. Okay. .encode. And then we get a UTF-8 in here. Cool. So if we do that, that should character.encode UTF-8. And that should get us the right value to pack into our data. Oops. All right, so that looks about right. So then if we set it to, so if we go into display pad worker and we want to set the main brightness to value equals 50. So then that ought to set the brightness to 50. So 32, yep. Okay. And then let's try 75 and make sure that it comes out as 4B. Which I believe it should. $4B. Okay, cool. So let's now that we've got the message packed properly, let's go ahead and send it to the device. I mean, it looks like it's already sending it to the device, but I don't think display pad worker. Let's try setting the brightness value to 0. Cool. Look, it turned it off. Here, let me get the cable all loosened up. Aha. All right, so you can see display is off, right? So let's go ahead and change this value back to 50. This is what I tried doing the other day and then I embarrassed myself, so. And this should turn it on. Hey, cool. So now we can set the brightness to various values. Let's try 100. 100. Yep. Trying to do this one-handed. Okay. All right, here we go. And hopefully that makes it brighter. I don't know, we'll see. Hey, that made it brighter. Cool. Hooray! All right, so we've got that going. Let's go ahead and let's stop short-circuiting our running function. And then what we can do is let's go in and set the I don't know. Do we want to set like a brightness value in the config or just have it as something that we can, I don't know. We should definitely go into the panel and set it up so that it can pull a brightness value from the config. And if it pulls a brightness value from the config, then we can set it. If it doesn't pull a brightness value from the config, then we'll just ignore it. That way, if the user wants to change the brightness or something, they can set it in their config, and then it would be per panel as well. So let's check. Where do we add this? All right. Okay. So this is where we're loading our config. Let's go ahead and self.brightness equals self.cfg json.get brightness. And then we will do what we probably want to do is set the brightness in here. So when we yeah, it should be when we change our panel. Right? I think that's yeah, this is the section that we need to do this in. So if our status is switched to a new panel, then what we'll do is we'll pull the brightness value from that panel config, and then we'll call the ggsetMainBrightness function. So then what we can do here is if active panel dot brightness, right? Device dot gg dot set main brightness value equals active panel dot brightness. Okay, so we'll go back into our panel. Save that, and then also double check. So this will get our self brightness value from the config. So let's go into obs.json, and let's go ahead and set up a brightness value. And we'll set this one to 100. And then let's go into our default and set a brightness value of 50. Brightness. And then that way we can test swapping between the two panels to see if it actually changes the brightness. So let's go ahead and reload this and see what it whines about. All right, let's go ahead and get this up so you guys can see all the action. Oh, oh. There we go. Cool. All right, now let's see if we can swap between these panels. Oop, wrong side. Swap between these panels and if it changes the brightness. Yep, so you can see right here it's sending our brightness command, and it should be setting the brightness lower. It's probably hard to see on the camera, but I can definitely tell in person that it's adjusting the brightness. So you could probably see like that little flicker. Cool. Neato. So now we've got that going. What else do we want to work on? I could probably go through and like the current activity suggests and clean up some of the code and work on some of the documentation. Actually real quick, let's do a commit. Git status. Git commit m updated brightness. And added docs. All right, and git push. All right, cool. And we will push that to Git. All right. So last thing I was working on, let's just real quick go through and look at this in Markdown. See what that looks like. Cool. Is this the right one? Right browser? Okay, cool. So I want to clean up this part a little bit, kind of define that a little bit more so that it makes more sense. But writing docs is boring. What other stuff do we have? Let me see, let me look at our goals. So we can add our checks for the environment variables, for our OBS WebSocket stuff. We could do state management for OBS event changes. Display updates, partial update, animations. So get set brightness, we could check that one off. We could do get device ID. get firmware version. Let's dig into those functions because those are kind of interesting. I also want to see if I can figure out the dump firmware function there is that this thing seems to have. So let's go and check our library that we've got going on. I've got this is my get firmware info function. Let's go look at the one that returns a serial number. I think that's this one. I think that's the get firmware info, but let's hop over into Windows and take a look at our PCAPs, because there's a bit right up here at the beginning. This one right here, I think. Yeah, this is the one that passes, or that returns like the GUID from the device. So, and the header for this one starts with 19. There's also one right here that starts with 19. I think this is the, like the get firmware data. I think what it's doing is calling the, get firmware information. Let's fire up ghidra and we will take a look. Welcome, welcome, those of you just joining. We're doing a little reverse engineering. Got a like a knockoff Stream Deck kind of thing with some buttons on it that doesn't have Linux support. So I'm reverse engineering it, trying to determine the USB protocol that that the native software talks to it with, and then write my own software in Python in Linux to do similar stuff. That way I can actually use it. Because I got a really good deal on it. It was like 35 bucks on sale at Micro Center. So, ghidra, did I click on this yet? I don't know. Whatever, we'll get 2 launches. Alright, that's going to take a second. Let's go back into Linux while that loads. And I believe, let's go look at the headers, because I did this in the past. Let's see if we've already got that one notated. I do not see it. Oh no, wait, here it is. Yeah, read sector memory. So that's the one that's actually reporting the serial number, the GUID. It's the read sector memory function, so we can dig into that one. Go back into Windows. We'll check it out in ILSpy. I think, do I already have that one kind of typed up yet? Oh yeah, here. Right here, I've sort of got that one typed up. So last I was messing with this one, it looks like the function has a couple parameters. We've got bin name, sector index, address, and length. Whether this works or not, I have no clue. But we can call it. I don't think I updated this one to work with the new interrupt setup. Yeah, because I'm still sending it to prep message, whereas, yeah, okay. We can update this to work with the new stuff. Cool. All right, looks like ghidra opened up. Go ahead and open up DisplayPad SDK. And then while that's loading, let's get ILSpy open. ILSpy with my little I. All right, so this one is what we're looking for. This is our read sector memory function that it's calling from the DisplayPad SDK.dll. And it is calling that function with a couple parameters, our I sector index, I address, I length, int pointer, and then I interval. Not sure what that is. And then the ID, which is like our device ID. So in ghidra, no, I don't give a shit, ghidra. All right, so let's go to our exports and go to read sector memory. And I believe, no, I have not named these yet. Okay. I'm at the stage where I'm making my own software. So I've been working on this project for like a few months now, off and on. I just started streaming it recently, but if we go back to Linux, this file right here, the mountain display pad file, has all of the reverse engineered functions that I've written. I've written these to basically emulate the messages that get sent to the device over USB. So all of these are the headers that I've kind of dissected from ILSpy and ghidra, and those correspond to the individual functions or the exports that are within the DLL. And then I've written a couple interrupt in and interrupt out functions to actually format the data and send it to the device. So what I've got so far is I've got the device working. I can send images to it, and I can read button presses if I have the software running, which I do not think I do. Yeah, so if I run this, it should reset, start doing some stuff. All right, so you can see it sends some data to the interrupt endpoints over USB, and I'm writing the whole image, like the whole picture and everything, with all the icons, and then the button presses get read by the software, and then it does stuff. So it's basically usable. If I want to go through and like kind of customize it and get it working for my purposes, I can, but I'm just kind of, I don't know. I'm still having fun messing with it and implementing things. So, and right now I'm trying to implement the read sector memory. There's this function right here in Windows in ghidra. This is the actual DLL file, the DisplayPad SDK. So this is what ships with the device from the manufacturer. They've got their software called Basecamp, Mountain Basecamp. This is what the manufacturer provided. They don't provide Linux support, so that's kind of the whole point in doing this, is to get it working in Linux. But this is their software, and I've gone through and determined that there's a couple important pieces of this, like the DisplayPad SDK.dll. This is what actually talks to the USB device, and then there's the Mountain DisplayPad worker, which is what talks to the DLL file. So one thing that really helped me out early on in this project was I found out that the Mountain DisplayPad worker.exe is actually written in C#, and I can use a tool called ILSpy to decompile that. And because C#, because when you compile a C# program, a lot of times the compiler doesn't strip the symbols out of the binary, and the symbols are things like this, like references to external libraries and stuff like that, and then also like the names of variables and parameters and functions. So none of that information gets stripped out by the compiler unless you tell it to. So by default, C# applications are very easy to decompile. And in this case, that helped us out because now I can see, hey, this tool or this program, the Mountain DisplayPad worker, is actually making calls out to the DisplayPad SDK, and it's calling these functions. And I can go through and kind of look at the logic of how that flows. But for now, what it's helping me with is it directs my my analysis in ghidra. So starting with like our read sector memory in ILSpy, we can see that it's calling that export from the DLL with a couple parameters, and it also even gives us our data type. So I'm going to go into ghidra and start labeling some of this stuff and trying to figure out how this read sector memory function works. I think I already set the No, I haven't set anything on any of this stuff, so let's get this up. So that's I sector index, I address, I length. I sector address. This is I length. And what was the other one? Or no, that was I address, I length. This is I length. And then we've got our pointer. This is our p data. I hope that helps, Prince. I kind of rambled on pretty quick, but if you have other questions, you just throw them at me. And then this last one is our ID and interval. All right, cool. And we'll have to do this again, I'm guessing, when we come in to this this call. Let's see. All right, so this is our read sector memory, and it's calling that with I sector address, I length, p data, I interval. So basically everything except for I address. It doesn't look like I address is included. Why is that? Where is that actually getting used? Oh, okay, so it's a calculation. And that's, I'm guessing, the max length of the memory, or the readable area of the memory. Overclock it so it runs Crisis. I don't know. Apparently this thing can do animations. Like you can like run animated icons or GIFs or something on it, which is something that I'd like to figure out how they do. So maybe we'll run Crisis on it in the future. You'll just have to subscribe to find out. I don't know. So this is, let's try to figure out what this function is doing before it calls the, I guess, the next routine or next part of this function. So this is all checking to get our handle from the device table. This is our pointer data. If it is null, then we return false. So we want to make sure that our pointer data actually points somewhere. And then if our sector address is less than 80, less than 50, not sure what that's supposed to be. And our address plus I length is less than, I'm assuming this is the max size of the readable region. And our I length is less than the readable region. So we can get some notes going. No. All right, so let's get a couple conditions. Just write these down because I will forget them. So the first thing that it's doing is it's checking if our address, I sector address, is, I guess, less than 80. The sector address less than 80. And let's see, address plus length is less than 4,000, was that 97? Yeah, 4,097. Which I'm guessing is 4,096 and then 97 for the Terminator. I'm not sure. And then we've got, and let's see, length. Oops. Length is less than 4,097. Okie dokie. So those are conditions. And then what it'll do is it will call read sector memory with a sector address and a length. P data. I'm guessing the P data is to hold the data that we get back from the device. Like it's a pointer to like our structure that stores that data, and then we have interval and then ID. So if we go into this, it's going to get a lot scarier. But let's start by naming our parameters. So we've got sector address, length, P data, interval, and ID. And this was a character, so let's change the type on that too. Is that a pointer to a character? Actually, let's just leave it undefined for now. Is this I sector address? And then that was what length? I length. And this is P data. That's our pointer data. And then this last one was what interval, and then ID. I interval. And this one is ID. Alright, so now what we can do is we can go through, we'll highlight this, we'll forward slice it, and we'll see how that's actually getting used and manipulated in our data. And then we can also compare this to our wireshark capture. So these, let's look for that 19. So yeah, here's the 19. That's our message header. So you can see in these messages that get sent to the device. So you can see right here the we're looking for the host. Where's the host sending that out? Should start up here. Here we go. Here's the first one. So our source is host. Destination is 1.2.4. That's our USB device. And then the message that we send out is our header, which is that 19, that hex value of 19. And we have a whole bunch of other crap like padding in here. And then we have our 1002, which is 10 and 02. So we've got a 10 and a 02 being passed to this function. So we can pretend that if we go back to, actually it should be from here. So we can pretend that like this sector address is like a 10, and then the next value, this length is 2. And that's our header. Actually, this might be backwards. It depends on how it packs it. That's one thing that's pretty confusing, is that ghidra doesn't really, decompiling isn't really like a surefire thing. So whenever ghidra goes through and it looks at this DLL file and tries to decompile it into like a readable sort of code, it'll kind of take its best guess at what this assembly is supposed to result in. If I knew more about the assembly, I could probably read this a little bit more directly and understand it some more. And I might have to, and we'll see about that. But hopefully not, because that's where it gets really confusing. Which step in reversing the USB protocol gave you the most headache? I would say that that's probably the send image data, or like set panel image, this one right here. And the reason why, and I can show you in the capture why that one gave me the most confusion, is because this right here, this is the one that starts with 21. This is the set panel image function. And you can see that it calls it with there's a bunch of, weird information and data in here that I don't understand the meaning of. And then it goes through and it does like a whole bunch of data back and forth between the host and the device, but it's all a bunch of zeros. So it didn't really like leave me a whole lot to like go on. And that was until I decided to write an entire red image to the device. And when I wrote an entire red image to the device, I noticed that these were no longer zeros and that they were actually Fs. They were like the hex value FF, which represented the RGB values of the red image. So that kind of helped narrow it down. And that's kind of the fun part, is you sort of like go back and forth between not knowing something and then just trying stuff and, getting the device to do things while listening to it until you eventually, piece together, the puzzle. And you figure out, oh yeah, that's what this is actually for. That's what that means. Now I can go back and, reapproach this analysis with a new context or a new, frame of mind. So that, honestly, that was probably the most confusing part. I mean, we'll see here in a minute when we get into like this read sector memory function, because this one seems pretty confusing too. It looks like the device is sending back, I'm guessing this is like the header, hey, I'm sending you back read device memory data. And then this 36 is like the, I guess the sector, like the memory address, but who knows? What I'm really after is like this GUID. I wanna be able to like pull this GUID off the device firmware, and then that way I can track it within my code, so that if you were crazy and you had more than one device, my code would support it. Totally unnecessary, but fun to do. So this function, I'm not too sure how it's packing these values. So I need to figure out what it's doing to pack these values into the message. We can see it's doing like some concatenation with this like extra out var and then bvar4, which is like some Boolean variable it's set somewhere. So like this send message. So yeah, I'm not too sure what all that's about. What's this local 50 value? I guess that's the point. That's a pointer to something. I don't know. But anyway, we're approaching 1 hour. I have to take a break real quick and go to the bathroom. So I'm going to give you guys some cool music to jam out to, and I will be back in just a couple minutes. Okie dokie. I'm back. Let's see, where were we? Got some fresh coffee. Some good old bean water. So, gotta read sector memory. Let's go back to our notes real quick. So checks our sector address is less than 80, and our address plus our length is less than 4097, and our length is less than 4097, and then it calls with the address, length, and then the pointer data. So we can assume that it's probably not going to be doing extra checks for length in this function. I mean, it might, but we'll see. So it shifts the value, does a bit shift on the I length by 8. So I guess it's packing this data in here. Let's go ahead and look at this first call that the host makes to the device. One of the things that I always have issues with for these functions so far is there doesn't seem to be any consistency in the way that it packs the message header along with the message data, like the parameters. So how many of these zeros are part of the header and how many of them are part of the parameters, I do not know. So we may have to do some back and forth, but it looks like got the interval, and then we have the length, 48, 49, 50. Actually, 1 second. All right, sorry about that. My cat was throwing up a hairball. Do you guys have cats? I'm sure sure you know all about that if you do. Okay. So, let's try to figure this out now. So we got our sector address, our length, and then our header. Let's try to piece these together based off the order of the local variable assignment. I think I'm not sure what the actual notation here in ghidra is. But this 19 is the first value. And I think we've got that is the second value in our actual packet. So I think we've got one byte with 19 in it. And then we have another byte that's just 0. And then we have our length, right? And then our interval. Well, let's look over here in the actual. So we call memset. 4, 7, okay. I need remedial assembly classes. So this is our EBP stack. Or no, that's our pointer. Throw our sector address on there, and then we throw our interval and our length. What is this? 4C. Byte pointer ESP. What's the AL instruction? That's add, right? Let's get our x86 reference. That's a register, right? I think that's a register. I don't know. It simply makes me feel like an idiot. Let's see if we can... Do we have this in... Actually, we could probably... Let's see if we can count how many of these packets there are. Prepares filter, selected, HED data. I wonder if I can do a splat. No. Yeah, I don't think so. Oh, I think we filter for the vendor data though. Prepares filter selected. There we go. Okay, so we look at, this is all the data that's coming back from the device. Let's see how many of those there are. Got 69 packets selected. And then if we look in here, let's check our see 10 in decimal, or sorry, 10 in hex is 16. See, I wonder if that's 1,002. I mean, is that the address, the start address, and then maybe there's some default values in the function? Let's check. Let's check if there are some default values. That probably would have been in the previous one, right here. If it was to set defaults. Yeah, I don't remember it doing that. Okay. So that's 1 byte in length. And that's also 1 byte in length. Okay. Maybe we can just try playing around with it in Linux. I'll start packing some of that stuff. Let's see if we can emulate this first one right here. Because I think what it's doing is the starting address is 0, and that's why we don't see any values in here for that. Like right here. It should be like the starting address. And then maybe this is the length and that's the interval? Oh, the interval was by default 2, wasn't it? Yeah, I interval is 2. So that's the default value. So that could be what this is. Right here. This 2 is the interval. And then 10, because it does do a shift. It does a bit shift on the length. So if the sector address is 0, but the length is like, I don't know, some other number. Let's go into CyberChef. CyberChef. And let's do bit shift. Bit shift left. Let's do 10. And shift it by 8. Let's see. Converts input string to hexadecimal. Let's see. 2 hex. Let's get hexadecimal chart. I just want to see the ASCII hex chart. Here's what I want. No, where is it? This one. Alright, so the hex value for 10, decimal of 16, characters daily, data line escape. I mean, I guess I could just copy that from wireshark, maybe. Yeah, okay. Let's see if that works. Then we'll come up here and we'll paste that. Do not think that is going to give us what we want. Okay. So you see where the vendor data ends. So vendor data is just one character. Wonder how long the sector address can be. Sector address, how big is that? Data wise. Maybe we can see over here. Because it's just an integer, right? Yeah, it's just an integer. Sector index. Okay. Yes, let's just play around in Python, see what we can get. Okay, so I read sector memory. Header length start index start address is the old notes that I had. All right, let's this gets our header. Sector index bytes. We make sure that it is. Oh, my libvirt crashed again. What the hell? Weird. Whatever. So I kind of want to comment out all of this this crap really quick just to test it. I'm going to take care of that too. What's up, Conrado? Conrado Fix. How are you doing? Let's see, print and ASCII.hexify message. I don't think I'm doing anything with bin name, am I? Let's take that out really quick. So get index, address, length. Then we'll do interval equals 2. Okay, and this will pack our header length, sector index bytes. Sector index bytes, and then address bytes. See, I don't think he was actually doing that. If we go back into Windows and look at ghidra. So sector address. Interesting. I wonder what the difference between sector address and address is. Oh, sector index, not sector address. Wow, that's a goof on my part. Sector index. And then address, so then it passes the index, length. Where does the address go? Are we not actually using the address anywhere? Address plus length? Yeah, but it's not actually passing it to the function. Okay, that's interesting. Well, what the hell is address? Can we see where this is actually getting called? Let's see, analyze, used by, display pad workers, read sector memory, used by, set device ID. Okay, let's look at this. So set device ID takes our device ID. String device GUID, new GUID, toString is device plug, does EP enable, long message, AP enable from set device ID. And then we got display pad read sector memory, device ID, previous value 2. Okay, so this is doing some other funky shit. Okay, so this is the part that's actually calling from the DLL file sector index, address number, sector index 0, address 0, number 4096. That's our pointer. And that's our interval. And then our device ID. So I guess it's calling 4096 as our length. Right? Number 2. If display pad SDK read sector memory. So it looks like it pulls the full memory. And it does partial copy, copies that value into pointer, and read sector memory value. Blah, 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 blah. Interesting. Okay. And this is definitely a little bit more helpful than just looking at the assembly. You can see like some of the default values that it calls it with. And that's the one at the very beginning, right? Yeah, this is number 49, so it's pretty early in the device setup. So I feel like this is probably the first one that gets called. So we're looking at the result of this. Is 4096 supposed to be in here somewhere? Is that what 1002 is? No. Doesn't make any sense. Okay. Let's check. Go into Linux, mess around with some hex values real quick. A equals 16. Print hex a. Well, that's not helpful. It's not hex, character. Of course, it's not going to be anything because it's a control character.